Hello class, this is Miss Aya with today's video on section 9.3 Convergence of Series. As you're watching the video, please remember to take down notes, writing down important vocabulary, formulas, equations, theorems, and examples. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what is occurring. And at the conclusion of watching the video, summarize what the video was about in your notes and submit that summary as well as an online question about the topic via the online WISC the night before class, not the moment before class. All right, let's begin. So if you remember, we're talking about geometric sequences, and we're going to sequences. This is a geometric sequence as well. And we're going to look at all the terms of the sequence. If we were to sum them up, what would they sum up to? Well, it's an infinite sequence, so we don't really know exactly what it's going to sum up to. So let's take a look at the first n sums of this sequence, and we call it a partial sum. And we can represent that partial sum S sub n by this exact same expression using the summation just from 1 to n, and it just sums up the first n terms. And if we look at a sequence of all the partial sums, we end up with a geometric series. So that's a review. And what we were looking at last time is whether or not a geometric series converges. And we say it converges to some value s if, as n goes to infinity, all the partial sums also tend to go towards that s. And then we say that the series converges. The series not a partial sum, but really the sequence, series of sums converges, and that a sum is s. If we cannot find a limit because a limit does not exist, then we say that the series diverges. And the series is the summation of a sub n, or the summation of the sequence of partial sums. All right, let's take a look at a simple example. And here we have a sequence, 1 over n times n plus 1. Most of you remember this as also the 1 over factorial sequence. Many ways to represent this sequence. And let's take a look at the first few terms of the sequence and add them up. As we can see, it looks very factorial, the terms. But if I take a look and start adding up the terms of the sequence, s sub 1 is 1/2, s sub 2 is 1/2 plus 1/6, s sub 3 is 1/2 plus 1/6 plus 1/12, I end up noticing that something interesting is going on. It seems like the partial sums have their own pattern occurring, and that pattern can be represented by the nth term by taking n over n plus 1. Now, this is what it seems like just from the first four partial sums. Is there a way that we can say for sure this will happen for all the partial sums of the sequence? And there is, using what's called induction, which is a method of showing it works for the simple case, n equals 1. 1 over 1 plus 1 is 1/2. And then assuming it works for n, any n, and then showing it works for n plus 1. So in other words, we have to show that s sub n plus 1 would be equal to n plus 1 over n plus 1 plus 1. And we can do that very easily using algebra as well here. The n plus 1 term of the sequence is, the n plus 1 partial sum is a result of the nth partial sum plus the next n plus 1 term of the sequence. And so this is the partial sum. And then this is an n plus 1 term. Remember, the sequence was 1 over n times n plus 1. And we do our algebra and we end up with this. So yes, we can prove that if it works for a case of the simple case, n equals 1, and if it works for n, then it'll work for n plus 1. Then yes, this term represents the sequence of partial sums. Well, knowing this sequence of partial sums, then we can easily see that this sequence of partial sums does converge, and it converges to 1. But graphically, what does that look like? It looks like this, and this is a good idea too, to kind of get an idea. As we can see here that the values of the sequence a sub n looks like this, and they're decreasing, but the values of the sums are increasing because it's a sum, but it never seems to hit 1. And we can use basic algebra to determine that. Few properties of series that we should be aware of. If I have two converging series, A and b, and let k be a constant, then I know several things. First of all, we proved this in a VA. The sum of the series is also converging, and it converges to the sum of the converging of the sequence. And the scalar multiple of a converging sequence also converges. And also number two, changing a finite number of terms in a series does not change whether or not it converges, although it may change the value of its sum. So for example, if I look at the sums from S sub 5 all the way to S sub infinity, and I show that those sums converge, then it really doesn't matter about sums that I didn't look at S1 through S4, because the actual series does converge. Now, where it converges to may differ based off the fact that I ignored the first 4 terms. So that's what that means. We also talked about, and this is a review, that if the sequence, the a sub n sequence, does not have a limit of 0 as n goes to infinity, or if the limit does not exist, then the series does not converge. In fact, it diverges. And the same thing, if I have a series that diverges, then multiplying it by a scalar number to give me another series, it won't also converge, it will diverge, as long as that k is not 0. All right, so let's take a look at how we can use series and integrals together, and this is really cool. So over here, we're going to start with a harmonic series, and by definition of harmonic, it's any series where the terms of the series get smaller and smaller and smaller, or tend to 0, but the sums of the series don't get smaller and smaller, and they don't tend to 0. Okay, I don't know if I explained it right. I'll go in detail a little bit later in class. So here we take a look at some of the examples of the partial sums, and as we can see here, that these values seem to be definitely are increasing, but are they bounded? Because even as it seems to be increasing very slowly. So what we're going to do is to figure out what the series sums, infinite sum, would be equal to. We're going to approximate just the first few terms. Well, we're going to approximate the infinite terms from using left-hand Riemann sums. So let's take a look at just an example of the first 3 terms. Now we're only using from n equals 1 to 4, and that's only because our nth terms, our sequence starts with n equals 1. Okay, and then we're going to just take a look at 3 terms, the first 3 terms. And here we have the rectangles have a height of the value at that n equals 1 and a width of 1. So the area of the rectangle is also the height of the rectangle. And as you can see here, based off how we drew it, the sum of the rectangles is going to be bigger than the area under the curve from 1 to 4. So let's take a look at the integral from 1 to 4 of 1 over x dx. Well, we know from our integration unit that that can be calculated as the definite integral of natural log of x from 1 to 4, and natural log of 4 minus natural log of 1, which is just 0. So basically this area is bounded on the bottom, the rectangle area is bounded on the bottom by natural log of 4. Why is that important? Well, we did it from 1 to 4. We can also say for S sub n, where n can be any number, not just 4, that we can describe this as being the area for the first n rectangles is going to be bigger than the area from 1 to n plus 1 of 1 over x dx, which we know to be natural log of this upper limit, which is n plus 1. So that lets us know that since this part over here is bounded, is not bounded, as n gets larger, natural log of n plus 1 gets larger, and we can say that as n goes to infinity, the partial sums do not converge. They get also larger and larger and larger, which lets us know that this is not a converging series. It's diverging. Will that be the same for a similar sequence, 1 over n squared? Well, we do the same process here. We take a look at the area under the curve is 1 over n squared. And we look at the left-hand integrals, but we actually can't look at the left hand. We're going to look at the right hand because of where the function is. And as you can see here, the right-hand Riemann sum integrals, the sum of these 4 rectangles is going to be smaller than the area underneath the curve. So this sum is going to be smaller than 1 to infinity of 1 over x squared. So how can I express 1 to infinity, the integral of 1 to infinity of 1 over x squared dx? Well, that's when we have to use what we know of integrals. So let's simplify this. We're trying to figure out what is the definite integral from 1 to infinity of 1 over x squared dx. So that's when we use our lovely powers of limits, which is as b goes to infinity, since we can't evaluate the limit at infinity, we let b go to infinity, and the integral from 1 to b of 1 over x squared dx, what does that look like? Well, it looks like this. And for those of you who don't know, if we let 1 over x be our u, then remember, this is the same as x to the negative 2, so that's why we have something like this, and that ends up being something that looks like this, the integration of from b to 1, which ends up being a value that as b goes to infinity, this value goes to 1. So then we can say that this limit is 1, which helps us out because if the upper bound limit is 1, and that means the sequence has a partial sum limit of 1. So let's summarize the integral test. If you have a sequence and if you have a function that is equal or models the terms of the sequence, and that function is decreasing, continuous, and positive, it lists continuous, but we need to include that. And then from 1 to infinity, if the function converges, then so will the sequence. And if the function diverges, then so will the series as well. Just a few reminders, n doesn't have to start at 1. We can let n be equal to any number bigger than 1. As long as f doesn't always have to be, it doesn't have to be decreasing always, but as long as it's decreasing for any x bigger than that n value. And also FYI, we call this a p series, so 1 over n to the p converges as long as p is greater than 1, and it diverges if p is less than or equal to 1. And there's a proof later on in the book. So let's look at our last example. So the sequence natural log of n over n, is that converging? Is that partial sum sequence converging? Well, before we can use the integral test, we have to determine whether or not this is a continuous function, whether it's a decreasing function, and then whether it's always positive. Well, of course we know that it's always going to be positive because the natural log of x is positive from x equals 1 to infinity, as well as natural log of x over x. Second thing is we do know that it's continuous because the function, again, we don't include in the domain that we're looking at is not 0, so we're good. Now the question is it always decreasing? And that may not be easy to determine. The quickest way to determine whether or not it's decreasing is to look at the first derivative of this function. If the first derivative of this function is always negative from when x is from 1 to infinity, then we can say it's decreasing. So we take the first derivative, and as x is bigger than 1, the denominator is always going to be positive, and 1 minus the numerator, 1 minus natural log of x is going to be negative. So therefore we can say that the first derivative is less than 0 when natural log of x is greater than 1, which is when x is bigger than some value e. So we can say that after at a certain point, any x bigger than e, you will always have the function values to be decreasing. Now that we have cleared that, then we can use the integral test to determine the summation or the convergence of the series. And so we do this using the limit form, and the limit as t goes to infinity from 1 to t of natural log of x over x. How do we take the integral of this? We use u substitution. Let u be natural log of x, and then dx over x is equal to du. And we have something that looks like that, and we can define it, and we can see that it goes to infinity. So very quickly, if it goes to infinity, then that means this integral is divergent, which means the series is also divergent. That's the end. I know that was quick.